Hello, friend. Welcome back. It's good to have you here again in this quiet corner of the night where the universe slows down just enough for us to listen. Some nights the sky feels heavier than it should. Stars breathe slower. Time folds in on itself soft and strange. And maybe that's not the mind playing tricks. Maybe that's the universe whispering something it's been trying to say for billions of years. Tonight, we're going to talk about death. But not the kind you're thinking of. Not the violent, explosive end. Not the supernova that tears through space like a scream. No. Tonight we're talking about the other kind. The gentle kind. The kind that takes its time, that glows softly, that turns endings into something almost beautiful. We're talking about red giants. The elderly stars. The ones that don't explode. They just breathe out slowly and let go. Before we begin this quiet journey together, if you find comfort in these slow drifts through the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell not for noise, but so the next quiet night can find you again. Now let's drift. Imagine this. 5 billion years from now, our sun, the same sun that warmed your face this morning, will begin to die. Not in fire, not in fury, but in a slow, inevitable expansion. It will swell, it will redden. It will become something we barely recognize, a red giant. And in that transformation, it will swallow Mercury. It will consume Venus. It will reach toward Earth with arms of plasma gentle but unstoppable like the tide coming in. But here's what's strange. Here's what keeps astronomers awake at night, staring at their data. This isn't destruction. Not really. It's transformation. It's the universe's way of recycling itself. Every atom of carbon in your bones, every breath of oxygen in your lungs, every flicker of iron in your blood, it all came from a star like this, a star that learned to let go. Red giants are the universe's gentle giants. They're what happens when a star runs out of the fuel it's been burning for billions of years. Hydrogen. The simplest element. The first element. The stuff that filled the universe right after the Big Bang. For most of a star's life, it fuses hydrogen into helium in its core, releasing energy, keeping itself inflated against its own gravity, staying balanced. But nothing lasts forever, not even stars. When the hydrogen in the core runs out, something beautiful happens. Something terrifying. The core contracts. It squeezes itself tighter and tighter, growing hotter and denser. Meanwhile, the outer layers, they do the opposite. They expand, they cool, they turn red. The star becomes huge, hundreds of times larger than it was. If our sun became a red giant right now, its surface would reach past Mars. Think about that for a moment. A single star swallowing 4 planets. Scientists suggest this process takes millions of years, not in a sudden flash, but in a gradual shift, like aging itself. The star doesn't know it's dying. It just follows the physics. Gravity pulls inward, pressure pushes outward, and when the balance changes, the star changes with it. Here's where it gets personal. Our sun is about 4.6 billion years old. It's middle-aged in stellar terms. It has another 5 billion years or so before it starts this transformation. That sounds like a long time, and it is. Longer than humans have existed. Longer than life has existed on Earth. But in cosmic terms, it's just a heartbeat, just a breath. And we know this will happen because we can see it happening right now to other stars. We can watch them swell and redden. We can measure their temperatures, their sizes, their compositions. We can trace their evolution backward and forward in time. We can see our own future written in their light. Take Betelgeuse. You might know it. It's the red supergiant in the constellation Orion, the Hunter's Shoulder. On a clear winter night, you can see it with your naked eye. A reddish dot flickering slightly. That star is dying. It's already a red giant, though technically a supergiant, because it started much larger than our sun. It's so big that if you placed it where our sun is, it would swallow everything out to Jupiter. Everything. And it's unstable. It dims and brightens irregularly. In 2019 and 2020, it dimmed so much that astronomers wondered if it was about to explode. It didn't. Not yet. But it will. Soon. In cosmic terms. Maybe tomorrow. Maybe in 100,000 years. We don't know. But our sun won't do that. Our sun isn't massive enough to explode. It will become a red giant, yes, but a gentler one. A quieter one. It will shed its outer layers slowly like petals falling from a flower. And what's left, the core, will become a white dwarf, a small, dense ember, still hot, still glowing, but no longer burning, just slowly cooling over trillions of years. There's a common mistake people make when they hear about red giants. They think red means cool, and in a way it does. The surface of a red giant is cooler than the surface of a normal star. Our sun's surface is about 5,500 degrees Celsius. A red giant's surface might be 3,000 or 4,000 degrees. Still hotter than any furnace we've ever built. Still hot enough to vaporize anything we could throw at it. But cooler, yes, and that's why it looks red. Temperature and color are connected. Hotter stars are blue. Cooler stars are red. It's the same physics that makes a flame blue at its hottest point and red at its edges. But here's the thing. Even though the surface is cooler, the core is hotter than it's ever been. As the core contracts under its own gravity, it heats up. It reaches temperatures of tens of millions of degrees. And eventually, if the star is massive enough, something ignites. Helium, the ash left over from burning hydrogen. It starts to fuse into carbon and oxygen. And that releases even more energy. A new kind of burning. A second life. This is called the helium flash in stars, like our sun. And it's one of the most violent events in stellar evolution. In just a few seconds, the core releases as much energy as the entire galaxy. But we can't see it. It happens deep inside, buffered by layers and layers of gas. The star barely flickers. From the outside, you'd never know. It's like an earthquake happening at the bottom of the ocean. The surface barely ripples. Some researchers believe this moment, this ignition of helium, stabilizes the star for a while. It becomes a little smaller, a little hotter on the surface. It moves to a different part of the Hertzsprung-Russell diagram, the chart astronomers use to classify stars. It settles into what's called the horizontal branch. And there it stays, burning helium in its core, burning hydrogen in a shell around the core for maybe 100 million years. A brief second wind, but nothing lasts. The helium runs out too, and when it does, the star swells again. Bigger than before, redder than before. It becomes what astronomers call an asymptotic giant branch star, an AGB star. And this is the final act, the last breath. The star becomes unstable. It pulses. It throws off mass in great gusts like an old man coughing. Stellar winds they're called, and they're fierce. They carry away entire Earth masses of material every few thousand years. Carbon, nitrogen, oxygen, all the elements forged in the core, all scattered into space. And here's the beautiful part. That material doesn't disappear. It drifts, it cools, it condenses into dust. And that dust becomes the seeds of new stars, new planets, new worlds. The death of one star is the birth of countless others. It's recycling on a cosmic scale. It's the universe's way of remembering nothing is ever truly lost. We are made of this. You and I. The calcium in our bones was forged in the core of a red giant. The iron in our blood came from a dying star. The oxygen we breathe was once part of a stellar wind drifting through the dark. We are quite literally stardust. Not metaphorically, not poetically, literally. And that's not a comforting thought. It's a staggering one. There's something humbling about realizing that our sun, this stable, reliable light that has warmed the earth for billions of years, will one day become one of these giants, that it will expand and cool and redden, that it will reach out and touch the orbits of its children, that it will, in a sense, devour the very worlds it helped create. But it will also give back. It will return to the cosmos everything it borrowed, and from that gift, new stars will rise, new Earths will form, new chances for life. The timeline feels distant, 5 billion years. We can't really grasp that. It's longer than the age of the Earth, longer than the existence of complex life, longer than the entire history of our species multiplied 1,000,000 times over. By the time the sun becomes a red giant, if humanity still exists, we won't be here. We'll have moved, evolved, changed beyond recognition. Or perhaps we'll be gone entirely, our story, just a thin layer in some distant planet's geology. But the sun will still be there, and it will still do what stars do. It will burn, it will swell, it will fade, and it will leave behind something beautiful. A planetary nebula, perhaps, a glowing shell of gas lit from within by the white dwarf core. Something future astronomers, if there are any, might look at and wonder about the way we look at the Ring Nebula or the Helix Nebula and wonder about the stars that made them. It seems as though the universe has a rhythm: birth, life, death, rebirth. Stars are born in clouds of gas. They live for billions of years burning steadily. And when they die, they give back everything they made. The clouds collapse again. New stars form. The cycle continues. And red giants are the transition, the bridge between endings and beginnings. They're not failures. They're not catastrophes. They're just part of the story, the long, slow exhale before the next breath. So, when you look up at the night sky and see a reddish star, think about what it might be. An elderly sun, swollen and cooling. A furnace of creation forging elements in its core. A giant, gentle, and inevitable breathing its last. And know that our sun will join them one day. Not soon, but someday. And when it does, it won't be the end. It'll just be a different kind of light. But what happens inside these giants? What forces shape them? What makes their cores contract while their surfaces expand? What happens to the planets that once orbited close, warm, and safe? Let's step closer. Let's look beneath the scarlet surface and see what makes a red giant breathe. The thing about stars is that they hide their deaths well. For billions of years, they burn steady and bright, and we assume they'll stay that way forever. But deep inside, something is always counting down, something quiet, something patient. And when the moment comes, the transformation isn't loud. It's inevitable. Picture a star like our sun, average, unremarkable, one of hundreds of billions in our galaxy alone. For most of its life, about 10 billion years, if it's lucky, it does one thing extraordinarily well. It fuses hydrogen into helium. 4 hydrogen nuclei slam together under immense heat and pressure, and they become one helium nucleus. The leftover mass, that tiny difference, becomes energy. Einstein's equation: E equals mc squared. Mass becomes light. Mass becomes heat. Mass becomes the reason we're alive. This happens in the core, the center, where temperatures reach 15 million degrees Celsius, where the pressure is so intense that matter behaves in ways we can barely simulate in our laboratories. Hydrogen atoms are stripped of their electrons. The nuclei bear protons move so fast they overcome their natural repulsion and fuse. And every second, our sun converts about 600 million tons of hydrogen into helium. Every second. For billions of years. But here's the problem. The core is small, only about 1/4 of the sun's total mass. And not all of that hydrogen can be fused. Only the innermost 10% or so gets hot enough. So eventually, after about 10 billion years, the hydrogen in the core runs out. Not everywhere, just in the center. And when it does, the fusion stops. Think about that for a moment. For 10 billion years, the star has been held up by the outward pressure of fusion. The radiation pushing out has balanced the gravity pulling in. Perfect equilibrium. But now, suddenly the center goes quiet. The fuel is gone. And gravity, patient gravity, finally wins. The core contracts. It has no choice. Without the outward pressure, it collapses under its own weight, And as it collapses, something strange happens. It heats up. This seems backwards, doesn't it? You'd think cooling would make something contract. But in stars, it's the opposite. When gas is compressed, it gets hotter. It's called gravitational heating, the same physics that makes a bicycle pump warm when you use it. Compression generates heat, so the core gets smaller and hotter. And meanwhile, just outside the core, there's still hydrogen, a shell of it. And now that shell is closer to the hot contracting core, close enough that it starts to heat up too. Close enough that fusion ignites there instead, not in the center anymore. In a shell around the dead helium core. This is called shell burning. And it's more efficient than core burning. The shell is thinner, hotter, more active. It produces more energy than the core ever did. And that energy has to go somewhere. It pushes outward. It inflates the outer layers of the star like a balloon. The star begins to swell. And as it swells, the surface moves farther from the core, farther from the heat source. It cools down. And a cooler surface radiates a different color, red instead of yellow. The star becomes a red giant. This isn't a quick process. It takes millions of years. The star doesn't suddenly pop into a giant. It gradually expands. The surface temperature drops from around 5,500 degrees to maybe 3,500 degrees. The radius increases by a factor of 100, maybe 200. If our sun went through this transition right now, its surface would extend past the orbit of Venus, maybe even Earth. Research shows this phase lasts about 1 billion years, a tenth of the star's total lifetime. And during that time, the star is unstable. It varies in brightness. It loses mass through stellar winds. It's no longer the steady, reliable fusion engine it once was. It's transitioning, dying slowly. There's a diagram astronomers use called the Hertzsprung-Russell diagram. It's a graph, temperature on one axis, luminosity on the other, and every star you can see falls somewhere on this chart. Most stars, including our sun, right now, sit on a diagonal line called the main sequence. That's where stars spend most of their lives, stable, burning hydrogen in their cores. But when a star runs out of core hydrogen, it moves off the main sequence. It drifts upward and to the right, brighter and cooler. It becomes a red giant. We've mapped this journey for thousands of stars. We know the path. We can predict it with remarkable accuracy. Stars like the sun will swell to about 200 times their current radius. Stars a little more massive will swell even more. Stars a little less massive will swell a little less. The physics is consistent, predictable, and sobering. Here's what's fascinating. We can watch this happen in real time, not to a single star because the process takes millions of years, but to populations of stars. Star clusters born together from the same cloud of gas, all roughly the same age. The more massive stars in a cluster evolve faster. They run out of hydrogen first. They become red giants first. And by studying clusters of different ages, we can piece together the entire sequence. It's like watching a time lapse of stellar evolution, but spread across the galaxy. Take the Pleiades, the Seven Sisters. A young cluster, maybe 100 million years old. All the stars are still on the main sequence, bright and blue. Now compare that to M67, an older cluster, about 4 billion years old. Some of the stars have already evolved into red giants. You can see them, scattered among the younger stars, reddish, bloated, different. Scientists suggest that our sun will begin this transition in about 5 billion years. The core will run out of hydrogen. It will contract and heat. The shell will ignite. The outer layers will swell. And Earth, if it's still here, will experience something no human has ever witnessed. A sky dominated by a red bloated sun. A sun that no longer fits in the daytime sky. A sun that stretches from horizon to horizon. The temperature on Earth will rise, the oceans will boil away, The atmosphere will be stripped by the intense radiation and the solar wind. The surface will become molten rock, and eventually, maybe the sun's outer layers will reach Earth's orbit and engulf the planet entirely. Or maybe Earth will survive, pushed outward by the loss of the sun's mass, the weakening of its gravitational pull. We don't know for certain. The calculations are close. Too close. But here's something people often get wrong. They think red giants are failures. They think the star is dying, and that's sad. But that's not the right way to think about it. The star isn't failing, it's evolving. It's doing exactly what the laws of physics require. And in the process, it's creating something new, the helium core, the heavier elements forged in the shell, the material that will eventually be scattered into space. Red giants are foundries. They're where the universe makes the elements necessary for life: carbon, nitrogen, oxygen. In the later stages of a red giant's life, helium fusion begins. 3 helium nuclei fuse to make carbon, 4 make oxygen. These elements didn't exist in the early universe. Only hydrogen and helium did. Everything heavier was made in stars, in red giants, in the shells and cores of dying suns. And when the star finally sheds its outer layers, those elements are released. They drift through space. They mix with clouds of gas. They become part of the next generation of stars and planets. And maybe, if the conditions are right, life. We know this because we can measure it. Spectroscopy, the study of light. When we look at the light from a red giant, we can see the fingerprints of elements in its atmosphere, absorption lines, dark lines at specific wavelengths. Each element absorbs light at different wavelengths. And by reading those lines, we can tell what the star is made of. Carbon stars, oxygen-rich stars, S-type stars with zirconium and yttrium. Each one tells a story of fusion, of creation, of transformation. There's a certain poetry in realizing that the death of a star is also a kind of birth, that the end of one thing is the beginning of another, that nothing in the universe is wasted. Everything is recycled, reused, reformed. The atoms in your body were once in a star, maybe a red giant. Maybe our sun billions of years from now will contribute atoms to some future world, some future being looking up at their own sky and wondering where they came from. Do you ever think about that? About the fact that you're temporary but the stuff you're made of isn't? That your atoms have been around for billions of years and will be around for billions more long after you're gone? The sun is ordinary, a yellow dwarf, G-type main sequence star, one of countless trillions. But it's also ours. It's the star that made our world possible. And when it becomes a red giant, it will unmake that world. But it will also contribute to new worlds, new chances, new stories. The timeline feels surreal, 5 billion years. The Earth is only 4.5 billion years old. Life has existed for maybe 3.8 billion years. Humans have been around for a few 100,000 years. Civilization for maybe 10,000. We can't grasp 5 billion, but it's there. Written in the physics, inevitable. And yet, even knowing this, there's something comforting about it. The sun will outlive us. It will outlive everything we build. It will outlive our species, our planet, our entire era of the universe. And when it finally does become a red giant, when it swells and cools and sheds its layers, it will do so in a universe still full of stars, still full of light, still full of the same laws that shaped it in the first place. It seems as though stars are the universe's way of thinking, slowly, over billions of years. They take simple matter and turn it into complexity. They create elements. They create energy. They create the conditions for life. And when they die, they pass on what they've made, a cosmic inheritance. But inside a red giant, there's more happening than just swelling and cooling. There's structure, layers, a hidden architecture of heat and pressure and fusion. There's a scarlet breath being drawn, held and slowly released. And if we want to understand what a red giant truly is, we need to step inside and see what it's made of. If you could slice a red giant open and see inside, You'd find something that looks less like a star and more like a paradox. The core dense and scorching, the envelope vast and cool, and between them, a thin shell of fire barely thicker than Earth, keeping the whole thing from collapsing. It's an architecture of extremes, a structure that shouldn't hold, and yet it does for millions of years, breathing in and out like something alive. Let's start with the obvious question. Why red? We've said the surface is cooler around 3,000 to 4,000 degrees Celsius. But what does that actually mean? Why does temperature change color? It comes down to blackbody radiation. Every object with temperature emits light. The hotter it is, the shorter the wavelength of light it emits most strongly. Our sun, at 5,500 degrees, emits most of its light in the yellow-green part of the spectrum. But it also emits blue and red, and when you mix them all together, it looks white to our eyes. A red giant cooler emits most of its light in the red and infrared. Less blue, less green, more red. It's the same reason a piece of metal glows red when it's heated in a forge. It's hot, yes, but not hot enough to glow white or blue. But here's what people misunderstand. They hear cool and think cold. They imagine a dying ember, fading, weak, and that's wrong. A red giant surface may be cooler than the sun's, but it's still hot enough to vaporize tungsten, hot enough to melt any spacecraft we could build, hot enough to ionize atoms. Cool is relative. In space, cool still means lethal. Now, let's go deeper. Past the surface, into the envelope. This is the vast bloated outer layer of the star. It can extend for hundreds of millions of kilometers. If our sun became a red giant and you were standing on Earth, assuming Earth somehow survived, the sun's outer atmosphere would be above you. You'd be inside the star. The density there is incredibly low, thinner than the best vacuum we can create in a laboratory, thinner than the space between planets, and yet it's still part of the star, still glowing, still hot. The envelope is mostly hydrogen and helium, the original material the star was born from. It hasn't been fused. It's just along for the ride pulled outward by the energy being generated below. And it's transparent, not like glass, but transparent to certain wavelengths of light. Radiation from the core, and the shell leaks through it slowly over thousands of years. Photons, packets of light scatter and bounce and drift, taking centuries to travel from the shell to the surface. By the time a photon leaves a red giant, it's ancient. Beneath the envelope, there's the hydrogen-burning shell. This is where the action is. A thin layer maybe just a few thousand kilometers thick, wrapped around the inert helium core. The temperature here is around 20 million degrees, hotter than the sun's core. The pressure is immense. And in this shell, hydrogen fuses into helium at a furious rate. More energy is produced here than the sun's core produces now. It's this shell that keeps the star inflated. It's this shell that defines a red giant. Research shows that the shell-burning phase is unstable. The shell isn't perfectly uniform. It develops pockets of higher and lower density. Convection currents form, hot gas rises, cool gas sinks. The star begins to pulse. Not violently, not like an explosion, but rhythmically, slowly. Over weeks or months, the brightness changes. The surface moves in and out like breathing. Astronomers call these pulsating red giants, Mira variables, long-period variables. Mira itself is a famous example. It's a red giant in the constellation Cetus the Whale, and it's been watched for centuries. In 1596, a Dutch astronomer named David Fabricius noticed it. It appeared brightened and then faded from view. He thought it was a nova, a new star, but it came back. It brightened again and again. Every 332 days, like clockwork. Mira pulses. At its brightest, it's visible to the naked eye. At its dimmest, you need a telescope. The star is breathing, expanding and contracting, and we've measured it. The radius changes by about 20%. The surface moves in and out by tens of millions of kilometers. Imagine that. a star inhaling and exhaling over the course of almost a year. And deeper still at the very center is the core, small, dense, dead. It's made of helium, the ash left over from billions of years of hydrogen fusion. And it's not burning, not yet. It's just sitting there compressed by the weight of the star above it, growing hotter and denser as the shell continues to dump more helium onto it. The core is roughly the size of Earth, but it contains about half the mass of the entire star. That's incomprehensibly dense. A sugar cube-sized piece of core material would weigh several tons. The core is held up not by heat or pressure, but by something quantum mechanical. Electron degeneracy pressure. Electrons' fermions can't occupy the same quantum state, and when you compress them enough, they push back, hard. This pressure doesn't depend on temperature. It's purely a result of the laws of quantum mechanics. The core is supported by the fact that electrons refuse to be squeezed any closer together. It's a strange kind of solidity, not like the solidity of rock or metal, but a solidity born from the rules of the very small. Scientists suggest this core will eventually ignite. When it reaches about 100 million degrees, helium fusion will begin. 3 helium nuclei will fuse to form carbon in a process called the triple alpha process. And that will release energy, a new phase of the star's life. But not yet. For now, the core just waits, inert, patient, growing. Let's talk examples. Real stars, red giants we can see and study. Aldebaran, the eye of Taurus the Bull. It's about 65 light-years away. A K-type giant, orange-red, 44 times wider than the Sun. If you placed it where the Sun is, it would swallow Mercury's orbit. Its surface temperature is about 3,900 degrees, cooler than the Sun, but its luminosity is 425 times greater. It's pouring out energy. And we've measured its mass. It's only about 1.16 times the Sun's mass, not much more. Most of the star is just empty space. Bloated gas, a thin atmosphere around a tiny core. Then there's Arcturus, the brightest star in the northern celestial hemisphere, 4th brightest in the entire night sky. It's a red giant, though it looks more orange, about 37 light-years away, 25 times the Sun's radius. Its surface temperature is about 4,300 degrees, a little warmer than Aldebaran, and it's moving fast. It's a high-velocity star, speeding through the galaxy at 122 kilometers per second relative to the Sun. That's unusual. Most stars in our neighborhood move much slower. Arcturus is probably an intruder, a star from a different part of the galaxy passing through. In about 1 million years, it'll be gone, too faint to see with the naked eye. Just a memory. And then there's Antares, the heart of Scorpius the Scorpion. A red supergiant. Technically not a red giant because it started much more massive, but the structure is similar, just bigger. Antares is enormous, about 700 times the Sun's radius. If you placed it at the center of the solar system, its surface would reach past the orbit of Mars, maybe even touch Jupiter. Its surface temperature is only about 3,500 degrees, deep red. And it's unstable. It's classified as a slow, irregular variable. Its brightness changes unpredictably. Sometimes it dims, sometimes it brightens. We don't fully understand why. What's striking about all these stars is their variety. Red giants aren't identical. Some are bigger, some are hotter, some pulsate, some don't. Some are rich in carbon, some in oxygen. The composition of a red giant's atmosphere depends on what's happening in the shell. If the star dredges up material from deeper layers, you get different elements. Carbon stars form when carbon from the core is mixed into the envelope. You can see it in the spectrum. Strong absorption lines from carbon molecules, Cn, C2. These stars look deep red, almost crimson. One common mistake is thinking all red giants are the same age. They're not. A star's evolution depends on its mass. A star more massive than the Sun will become a red giant faster. A star less massive will take longer. A star with 1.5 solar masses might become a red giant in just 3 billion years. A star with 0.8 solar masses might take 15 billion years, more than the current age of the universe. Those stars haven't had time to evolve yet. Every red giant in the sky started with a different mass. They're all at different points in their journey. Here's something else. Red giants are not spherical, not perfectly. The rapid rotation some of them had when they were younger has slowed down, but not completely. As the star expands, conservation of angular momentum means the surface rotates even slower, but there's still some rotation, and that creates bulges, equatorial bulges. The star is slightly flattened. Oblate. We've measured this with interferometry, instruments that combine light from multiple telescopes to create ultra-high-resolution images. We can resolve the surfaces of nearby red giants. We can see their shapes. We can map their spots, their convection cells, regions of rising and sinking gas. Betelgeuse, for instance. We've imaged it. We've seen bright spots on its surface, hot regions, maybe giant convection cells like the granules on the Sun, but vastly larger. Each cell might be bigger than the Sun itself. We've also seen asymmetries. The star isn't perfectly round. It's lumpy, irregular, and it's ejecting mass unevenly, creating plumes and clouds around it. It seems as though red giants are messy. They're not the clean, symmetric objects we imagine stars to be. They're dynamic, chaotic. They pulse and flicker. They lose mass. They change shape. They're dying, yes, but not quietly. They're going through something turbulent, something beautiful in its complexity. And the color, that scarlet glow. It's not just physics, it's also history. When you look at a red giant, you're seeing a star at the end of a long journey, a star that has burned steadily for billions of years, a star that has run out of fuel and now in its final act is creating something new, heavier elements, carbon, oxygen, the building blocks of planets, of life. Every red giant in the sky is a forge, a factory, taking helium and turning it into something more complex. And when the time comes, when the outer layers are finally shed, those elements will drift into space. They'll mix with hydrogen clouds. They'll condense. They'll form new stars, new worlds, and the cycle will continue. But the core is still waiting, still growing denser, still heating up. And when it finally reaches that critical temperature, when helium fusion ignites, something remarkable will happen, something violent and hidden. A flash of energy so intense it rivals the output of an entire galaxy. And that moment, that sudden awakening, changes everything. There are moments in the universe that happen only once. Moments so brief, so hidden, that even if you were watching, you'd miss them. The helium flash is one of those moments. It lasts a few seconds, maybe minutes. Deep in the core of a red giant buried under layers of gas, thicker than the distance from here to the moon, 100 million degrees of heat finally crosses a threshold. And helium, the ash of hydrogen burning the leftover dust of 10 billion years, ignites. Imagine waiting 1 billion years for something to happen, not watching, not expecting, just existing in a state of compression growing hotter, degree by degree, until one day without warning, everything changes. That's what the helium core does. It waits, silent, inert, patient beyond measure, and then it wakes. The physics is delicate. Helium is harder to fuse than hydrogen. It takes more energy, more heat, more pressure. Hydrogen nuclei protons are single particles. Positively charged, yes, and they repel each other, but they're small. They can get close. At 15 million degrees, they fuse. Helium nuclei alpha particles are bigger. 2 protons and 2 neutrons bound together. And they're doubly charged. The repulsion is stronger. You need higher temperatures to overcome it, around 100 million degrees. And you need density. Lots of it. More particles crammed into less space. In a red giant's core, the density is staggering. We're talking about 100,000 times denser than water. A teaspoon of core material would weigh as much as a car. And it's all helium, helium-4 specifically, as stable, unreactive, just sitting there, supported not by heat, but by quantum pressure, electron degeneracy. The fact that electrons can't be squeezed into the same state. But as the hydrogen shell keeps burning, it keeps adding more helium to the core, more mass, more compression. And the temperature rises, slowly, inexorably, 1 degree at a time. And when it finally hits that magic number around 100 million degrees, something extraordinary happens. 3 helium nuclei collide, not 2. 3, and they fuse into carbon, carbon-12. This is called the triple alpha process. Alpha particles, helium nuclei, 3 of them becoming carbon. It sounds simple, but it's not. The probability of 3 particles colliding at exactly the same moment is tiny, almost 0, and yet it happens. Because there's an intermediate step. First 2 helium nuclei fuse briefly into beryllium-8. Beryllium-8 is unstable. It falls apart almost immediately, in about 10 to the minus 16 seconds. But if in that impossibly short window, a 3rd helium nucleus collides with it, you get carbon-12. And carbon-12 is stable, it lasts. And in the process, energy is released. This was a mystery for decades. Scientists in the 1950s couldn't figure out how carbon existed at all. The math didn't work. The probability was too low. Until Fred Hoyle, a British astrophysicist, made a prediction. He said there had to be an excited state of carbon-12 at a very specific energy level, a resonance, something that would make the triple alpha process much more likely. And he was right. Experiments confirmed it. There's an energy level in carbon-12 at 7.656 mega-electron volts. And that resonance, that precise match, makes carbon production possible. Some believe this is one of the most remarkable fine-tunings in the universe. If that energy level were just slightly different, carbon wouldn't form. And without carbon, there'd be no life. No DNA, no proteins, no us. The universe would be lifeless. Just hydrogen and helium, stars and gas, nothing complex, nothing aware. But back to the core. The helium ignites, and when it does, it releases energy. A lot of energy. In a fraction of a second, the core produces as much power as an entire galaxy. Billions upon billions of stars worth of energy, all concentrated in a sphere the size of Earth. You'd think this would tear the star apart, and in a way it tries to. The core heats up. The pressure rises. The temperature spikes to hundreds of millions of degrees. Energy floods outward. But here's the thing. The core is degenerate. It's supported by electron pressure, not thermal pressure. And degenerate matter doesn't behave the way normal gas does. When you heat normal gas, it expands. Expansion reduces the density. Reduced density slows the reaction. It's a natural thermostat, self-regulating. But degenerate matter doesn't expand when you heat it, not immediately. The pressure comes from quantum mechanics, not temperature. So, the core heats up without expanding, and that makes the fusion rate increase. More fusion, more heat. More heat, more fusion. It's a runaway reaction. For a few seconds, maybe a few minutes, the helium burns out of control. This is the helium flash. And it's one of the most violent events in stellar evolution. But you'd never see it, not from outside. The energy is trapped deep in the core, buffered by layers and layers of gas. By the time it reaches the surface, millions of years later, it's spread out, diffused. The star doesn't explode. It doesn't brighten suddenly. From the outside, nothing seems to change. Research shows that the helium flash releases about 10 to the 46 joules of energy. That's roughly the sun's total energy output over 200 million years, released in seconds. It's hard to even comprehend that scale. And yet the star survives. The core eventually expands. Once enough energy has been dumped into it, the degeneracy breaks. The core starts to behave like normal gas again. It expands, cools slightly, and the fusion rate stabilizes. After the flash, the star enters a new phase. Helium burns steadily in the core. Hydrogen still burns in a shell around it. The star is now powered by two sources of fusion, and it settles down. It becomes a little smaller, a little hotter on the surface. It moves to a different part of the Hertzsprung-Russell diagram, the horizontal branch, and there it stays for maybe 100 million years, a brief second wind. But not all stars experience the helium flash the same way. It depends on mass. Stars like the Sun, with masses between about 0.5 and 2 solar masses, have degenerate cores. They experience the flash, but more massive stars don't. Their cores are hot enough and dense enough that helium ignites smoothly without degeneracy. No flash, just a gradual transition from hydrogen burning to helium burning. Quieter, less dramatic, and stars less massive than about half the Sun's mass. They never ignite helium at all. They're too small. They don't compress the core enough. They become white dwarfs, directly skipping the red giant phase entirely. But those stars take longer than the current age of the universe to evolve. None of them have finished yet. They're still burning hydrogen, still on the main sequence. Here's something people often misunderstand. They think the helium flash is like a supernova, a massive explosion, and it's not. It's hidden, internal. The star doesn't blow up. It doesn't shed mass. It doesn't brighten. The only way we know it happens is through models, simulations. We can't observe it directly. We can only infer it from the before and after states. Think about that for a moment. One of the most energetic events in a star's life, and we've never seen it. We've only calculated it, predicted it, trusted the math. And the math says it happens. Every sun-like star, when it becomes a red giant, will experience this moment, this hidden explosion, this brief violent awakening of its core. The triple alpha process, once stable, produces carbon. And if the temperature is high enough, carbon can capture another helium nucleus and become oxygen-16. So, the core becomes a mix. Carbon and oxygen, the two elements most essential for life as we know it. And they're being forged in the heart of a dying star, quietly, steadily, for 100 million years. There's a certain elegance in the way the universe builds complexity. Hydrogen fuses to helium in the main sequence. Helium fuses to carbon in red giants. Carbon fuses to heavier elements in more massive stars. Each stage requires higher temperatures, higher densities. Each stage produces new elements, and each stage is shorter than the last. Hydrogen burning lasts billions of years. Helium burning lasts 100 million. Carbon burning in massive stars lasts just a few thousand years. The universe speeds up as it builds. And all of these processes are governed by the same fundamental forces. The strong nuclear force binding protons and neutrons together. The electromagnetic force making them repel. Gravity pulling everything inward. Quantum mechanics preventing total collapse. It's a balance, a dance. And the rules are written into the fabric of reality itself. Let's think about temperature for a moment. 100 million degrees. What does that even mean? At that temperature, atoms don't exist. Electrons are stripped away. Nuclei move at a significant fraction of the speed of light. Matter is a plasma, a soup of particles colliding, fusing, radiating. We can't create those conditions on Earth. Not sustainably. Not yet. Fusion reactors get close, for a fraction of a second. But a star does it continuously, for eons. Do you ever wonder what it would be like to witness something like the helium flash, to be there somehow, in the core watching the moment helium ignites? Of course you'd be vaporized instantly, crushed, ionized. But imagine the light, the heat, the sheer intensity of creation happening all around you. It's almost sacred. Scientists suggest that the helium flash might not be perfectly uniform. There might be pockets, regions where fusion starts first. And those pockets might create instabilities, waves, pulses that propagate through the core. We don't know for sure. The models are complex. The physics is at the edge of what we can simulate. But it's possible. And if it's true, then the core of a red giant in those first moments of helium burning is not just energetic, it's chaotic, turbulent, alive with motion. And then it calms. The runaway stops. The core expands just enough to regulate itself, and the star settles into a rhythm. Helium burning in the core. Hydrogen burning in a shell. The outer layers still bloated, still red, but now more stable. The star has found a new balance, a temporary one. This phase doesn't last long, not compared to the main sequence. 100 million years sounds like a lot, but it's only 1% of the star's total lifetime. A brief pause, a moment of stability before the next transformation. Because helium, like hydrogen, eventually runs out. And when it does, the core will contract again, heat again, and the cycle will repeat. But differently, more violently, more unstable. It seems as though stars are engines of transformation, each stage building on the last, each phase producing something new. And the helium flash is the moment of transition, the moment the star moves from one kind of life to another, from hydrogen burner to helium burner, from main sequence to horizontal branch, from youth to middle age. But while all of this is happening deep inside, something else is unfolding on the outside. The red giant's outer layers, those vast bloated atmospheres, are not passive. They're being shaped, sculpted, torn away, and the worlds that once orbited safely are now in danger. The horizon is closing in, and for the planets there is no escape. Imagine waking up one morning and the sun has doubled in size, not over millions of years. Just suddenly in your lifetime, it's bigger, redder. The sky at noon looks like sunset, and it keeps growing. Day by day, week by week, the heat intensifies. The oceans begin to steam, and you realize with absolute certainty that there is nowhere to run. This is what the inner planets will face when our sun becomes a red giant. Mercury first, then Venus, and then maybe Earth. Planets don't get a vote. They don't get to move. They're locked in their orbits by gravity, by momentum, by the physics that has kept them circling the sun for 4.5 billion years. And when the sun changes, when it swells into a red giant, those orbits become death sentences. Let's start with Mercury, the closest planet, the smallest. A barren, cratered world that's already scorched by the sun's heat. Surface temperatures on the day side reach 430 degrees Celsius, hot enough to melt lead. But when the sun becomes a red giant, Mercury won't melt. It'll vaporize. The sun's outer atmosphere will reach past Mercury's orbit. The planet will be inside the star. Friction from the tenuous gas will slow it down. Its orbit will decay. And within a few thousand years, maybe less, Mercury will spiral inward and be consumed entirely. Vaporized, dissolved, mixed into the sun's outer layers. Venus is next. A planet almost Earth size, shrouded in thick clouds of sulfuric acid. Surface temperature 465 degrees hotter than Mercury, thanks to a runaway greenhouse effect. But Venus won't survive either. The sun's expansion will engulf it. The atmosphere will be stripped away first, blown off by the intense radiation and the solar wind. Then the surface will melt. The rock will turn to lava, and finally the planet itself will be swallowed. It'll share Mercury's fate, a slow death by immersion. And then there's Earth, our world, the only place we know of with life. No, the calculations are close, too close. Some models suggest Earth will be engulfed. Others suggest it will survive just barely at the very edge of the sun's atmosphere. It depends on how much mass the sun loses during the red giant phase. And the sun will lose mass. A lot of it. Maybe 30% of its total mass. blown away by stellar winds. When a star loses mass, its gravitational pull weakens, and the planets, all of them, drift outward. Their orbits expand. It's a slow process, but it's measurable. Research shows that Earth's orbit could move outward by about 50%, from 150 million kilometers to maybe 225 million kilometers. And that might be enough. Enough to keep Earth just outside the sun's reach. But survival doesn't mean safety. Even if Earth isn't swallowed, it will be destroyed. The temperature will rise to thousands of degrees. The atmosphere will be stripped away. The oceans will boil off into space. The surface will become molten rock, lava oceans. No water, no air, no life, just heat and radiation and silence. Earth will become a scorched, lifeless husk, a dead world orbiting a dying star. There's something deeply unsettling about imagining Earth's future this way. We think of our planet as eternal, stable, safe, but it's not. It's temporary, fragile. And the sun, the source of all life, will one day become the instrument of Earth's destruction. Not out of malice, not out of anger, just physics, just time. Some believe this is a reminder that all life, has an expiration date. Not just individual lives, not just species, but all life on a planet, all ecosystems, all the complexity that took billions of years to evolve. One day it will end. Not from asteroids or supervolcanoes or climate change, but from the star itself, the very thing that made life possible. But let's think about the outer planets: Mars, Jupiter, Saturn, Uranus, Neptune. What happens to them? Mars is far enough that it won't be engulfed, but it will heat up a lot. The frozen carbon dioxide at the poles will sublimate. The thin atmosphere will thicken briefly. Temperatures could rise to habitable levels. For a few million years, Mars might have liquid water again. Oceans, rain, maybe even a second chance at life. But it won't last. When the sun sheds its outer layers and becomes a white dwarf, Mars will freeze again. Colder than it is now. Darker, dead. Jupiter and the outer giants are safe, relatively speaking. They're too far away. The sun's atmosphere won't reach them, but they'll change too. Jupiter will warm, its atmosphere will expand, its storms will intensify. The Great Red Spot, that massive anticyclone, might grow even larger. And Jupiter's moons, those icy worlds, will melt. Europa's subsurface ocean will become a surface ocean. Ganymede and Callisto will thaw. For a brief period, these moons might be warm enough for liquid water, warm enough for life, if anything could adapt fast enough. Scientists suggest that some of Jupiter's moons could become temporary habitable zones, places where life, if it exists, could thrive for a few million years. And then, when the sun fades, they'll freeze again. It's a strange thought. That life might migrate, not between planets, but between moons, following the warmth, following the light, adapting to a universe in transition. And then there are the exoplanets, planets orbiting other stars. We've discovered thousands of them, and some of them orbit red giants, or stars that used to be red giants. These planets survived, somehow. We don't know how. Maybe they were farther out. Maybe their stars lost enough mass. Maybe they migrated outward. But they're there. Proof that not every planet dies when its star becomes a red giant. One example is a planet orbiting a star called V391 Pegasi. It's a hot subdwarf star, the core remnant of a red giant that has already shed its outer layers. And there's a planet, a gas giant, orbiting it at about 1.7 astronomical units. That planet survived the red giant phase. It was probably closer initially, maybe where Earth is now, but it migrated outward as the star lost mass, and now it orbits a white dwarf precursor, a survivor. This gives us hope, not for Earth necessarily, but for the idea that planetary systems can endure stellar evolution, that some world somewhere might outlast their star's red giant phases. That life, if it's clever enough, if it's resilient enough, might find a way to survive. But here's a question. Could humanity survive? Could we as a species outlast the sun's transformation? 5 billion years is a long time, longer than life has existed on Earth, longer than multicellular organisms have existed. By the time the sun becomes a red giant, humanity will either be extinct, evolved into something unrecognizable, or spread across the galaxy. We won't be here, not on Earth, not in this solar system. And maybe that's okay. Maybe the point isn't to survive forever in one place. Maybe the point is to spread, to adapt, to become something that doesn't depend on a single star, a single planet, a single moment in time. There's a concept in astronomy called the habitable zone, the region around a star where liquid water can exist on a planet's surface. For our sun, right now that zone stretches from about 0.95 astronomical units to 1.37 astronomical units. Earth is at 1 astronomical unit, comfortably in the middle. But when the sun becomes a red giant, the habitable zone will shift outward dramatically. It might reach from 7 astronomical units to 22 astronomical units, somewhere between Jupiter and Saturn, and it will stay there for maybe 100 million years before the sun sheds its layers and the zone disappears entirely. Some researchers have calculated that the habitable zone around red giants is actually quite large, larger than around main sequence stars. Because red giants are so luminous, they pour out enormous amounts of energy, and that energy warms a huge region of space. If a planet or moon is in the right place, it could be habitable, warm, wet, alive. But there's a catch. The habitable zone doesn't last long. 100 million years sounds like a lot, but it's not enough for complex life to evolve from scratch. Life on Earth took 3.5 billion years to go from single cells to intelligent beings. 100 million years is barely enough for multicellular life to develop. Maybe not even that. So any life that exists in a red giant's habitable zone would have to have started earlier. Migrated from farther in. Adapted quickly. And there's another problem. Tidal locking. Planets and moons close to a red giant, especially in the habitable zone, would likely become tidally locked. One side always facing the star, one side always in darkness. The day side would be scorched, the night side would be frozen. Only a narrow band around the terminator, the line between day and night, might be habitable. A thin ring of twilight, forever. Imagine living on a world like that, where the sun never moves, where half the sky is always bright and the other half always dark, where you can walk from eternal day to eternal night in a few hundred kilometers. It would be alien, beautiful, terrifying. It seems as though the universe offers no guarantees. Planets form, they orbit, they evolve, and when their star dies, they die too. Or they adapt, or they move, or they're destroyed. There's no sentimentality, no mercy, just physics playing out over billions of years. And yet, there's something almost poetic about it. The idea that Earth, this pale blue dot, this cradle of life, will one day be consumed by the very star that gave it life. That the sun will reclaim the world it illuminated for so long. That the atoms that made up forests and oceans and people will be scattered into space, mixed with stellar gas, and become part of something new. We are, in a very real sense, temporary tenants, borrowing matter from the universe for a brief moment, using it to think, to feel, to wonder, and then giving it back. The sun made us, and the sun will unmake us. And from that unmaking, something else will rise. But the destruction of planets is only part of the story, because while the sun is swallowing worlds, it's also creating something. A wind, a stream of particles flowing outward, carrying away mass, carrying away elements, sculpting the space around the star. And that wind, gentle but relentless, is carving the cosmos into something new. There's a current flowing through space right now, invisible, silent. A river of particles streaming away from every star, including our sun. Protons, electrons, helium nuclei, moving at hundreds of kilometers per second. We call it the solar wind, and it's gentle, barely noticeable. But when a star becomes a red giant, that gentle breeze becomes a gale, a torrent, a flood of matter pouring into space, carrying away entire planets' worth of mass every few thousand years. The solar wind we experience now is weak. About 1 million tons of material per second leaves the sun. That sounds like a lot, but the sun is massive. 99.8% of all the mass in the solar system. 1 million tons is nothing. It would take hundreds of billions of years to blow away the sun at this rate. The sun doesn't even notice. But red giants are different. Their winds are fierce. A red giant can lose 1/10,000th of a solar mass per year. That's 100,000 times stronger than the sun's current wind. In just 1 million years, a red giant can shed 10% of its mass. In 10 million years, maybe 30 or 40%. Gone, blown away, scattered into the galaxy. This isn't an explosion. It's not violent in the way we usually think of violence. There's no shockwave, no blast, just a steady, relentless outflow. Particles streaming away at 10 to 30 kilometers per second, slow by cosmic standards, but unstoppable. And over time, it strips the star down to its core. The mechanism is fascinating. It starts with radiation pressure. Light has momentum, not much. But when you have as much light as a red giant produces, it adds up. Photons, packets of light, are absorbed by atoms in the star's outer atmosphere. And when they're absorbed, they transfer their momentum. They push. And in the outer layers of a red giant, where the gas is thin and the gravity is weak, that pushes enough to lift material away from the star. But there's more. Dust forms in the outer atmosphere. Tiny grains, carbon, silicates, oxides. These grains are opaque. They block light. And when they block light, they absorb even more momentum. They're pushed outward faster. And as they move, they drag gas with them. It's like a sail catching the wind. The dust particles are the sail. The light is the wind. And the gas is pulled along for the ride. Research shows that the rate of mass loss depends on the star's luminosity and temperature. The brighter the star, the stronger the radiation pressure. The cooler the star, the easier it is for dust to form. Red giants are both. Extremely luminous, extremely cool at the surface. Perfect conditions for strong winds. And the wind carries everything. Hydrogen, helium, carbon, nitrogen, oxygen. All the elements that were forged in the core and dredged up to the surface. All the products of fusion. All the building blocks of planets and life. Scattered into space, mixed with the interstellar medium, recycled. This is where the heavier elements come from. Not just in our solar system, everywhere. Every atom of carbon in your body was made in a star. Probably a red giant. Every breath of oxygen, every fragment of nitrogen in your DNA. Stars create these elements through fusion, and stellar winds distribute them. Without stellar winds, the universe would be sterile, just hydrogen and helium. No complexity, no chemistry, no life. Let's think about carbon for a moment. Carbon is the fourth most abundant element in the universe after hydrogen, helium, and oxygen. But it wasn't always there. In the first few minutes after the Big Bang, only hydrogen, helium, and a trace of lithium formed. Everything heavier had to be made in stars, and carbon is primarily made in red giants, through the triple alpha process, helium fusing into carbon. But making it isn't enough. It has to get out. And that's where the stellar wind comes in. As the red giant evolves, convection currents develop. Hot material from deeper layers rises to the surface. Cool material sinks. And in some red giants, this convection is so strong that it dredges up carbon from the core. It mixes it into the outer layers. And then the wind carries it away. These are called carbon stars. You can recognize them by their deep red color, almost crimson, and by their spectra, strong absorption lines from carbon molecules, CN, C2CH. These stars are factories, churning out carbon and releasing it into space. And that carbon billions of years later might become part of a planet, part of a molecule, part of you. Some believe that without stellar winds from red giants, planets like Earth wouldn't exist, at least not in their current form. The solar nebula, the cloud of gas and dust that collapsed to form the sun, and planets contained elements heavier than helium. And those elements came from previous generations of stars. Stars that lived, evolved into red giants, shed their outer layers, and seeded the galaxy with the raw materials for new worlds. There's a beautiful circularity to it. Stars are born from gas clouds enriched by previous stars. They live. They create new elements. They die and return those elements to the gas clouds, and new stars form, richer, more complex, with more heavy elements. Generation after generation, the universe becomes more chemically diverse. Astronomers measure this with something called metallicity, the fraction of a star's mass that's made of elements heavier than helium. In astronomy, anything heavier than helium is called a metal, even oxygen, even carbon. It's a strange convention, but it works. The sun's metallicity is about 2%. 2% of its mass is metals. The rest is hydrogen and helium. But the very first stars, the ones that formed right after the Big Bang, had zero metallicity. No metals at all, just hydrogen and helium. And when they became red giants, if they did, they had nothing to distribute except helium. No carbon, no oxygen, nothing useful for planets or life. But their deaths enriched the next generation. And that generation enriched the next. And over billions of years, the metallicity of the galaxy increased. Now, let's talk about the wind's structure. You might think it's uniform, a smooth flow in all directions, but it's not. Stellar winds are clumpy, irregular. They have density variations, streams, and gaps. Some of this is caused by the star's rotation. As the star spins slowly, the wind gets wound up. Like water spiraling down a drain, it forms a spiral pattern. We've seen this around some red giants, spiral structures in the gas, evidence of rotation. And some red giants pulsate. They expand and contract rhythmically. And when they do, the wind varies. When the star expands, the wind strengthens. More surface area, more radiation, more push. When the star contracts, the wind weakens. This creates shells, layers of denser and less dense gas, like ripples in a pond, moving outward at the speed of the wind. One famous example is Mira. We talked about it earlier, a pulsating red giant. And Mira has a tail, a comet-like tail of gas stretching behind it as it moves through space. The wind blows backward, pushed by Mira's motion through the interstellar medium. And that tail is 13 light-years long. 13. That's 3 times the distance from the sun to the nearest star. A trail of material glowing faintly marking Mira's path through the galaxy. Scientists suggest that Mira is losing about 1 Earth mass of material every 10,000 years. Over its lifetime, it might lose half its mass, maybe more. And all of that material, that carbon and oxygen and nitrogen, will drift through space. It will cool. It will condense into dust. And eventually it will become part of a molecular cloud, a stellar nursery, where new stars are born. Here's something people often get wrong. They think stellar winds are hot, because the star is hot. But actually, the wind cools as it expands. By the time it's a few stellar radii away, the temperature has dropped to a few hundred degrees. And farther out, it's even cooler, cold enough for molecules to form, cold enough for dust to condense. The wind isn't a blast of heat. It's a flow of matter that cools and transforms as it travels. And the dust at those tiny grains, they're important. They're the seeds of planets. When a molecular cloud collapses to form a new star, the dust grains stick together. They grow, they collide and merge. Over millions of years, they become pebbles, boulders, planetesimals, planets. Every planet in our solar system, including Earth, is made from dust that came from stellar winds, from red giants, from stars that died long before the sun was born. Do you ever think about that? That the ground beneath your feet, the air you breathe, the water you drink, all of it was once part of a star, that every atom in your body has traveled through space for billions of years, moving from star to cloud to planet to you. It's a humbling thought, and a connecting one. We're not separate from the universe. We're part of it, made of it. The wind also shapes the space around the star. It creates a bubble, a region where the stellar wind dominates. Inside the bubble, the gas is hot ionized, moving fast. Outside the bubble, the interstellar medium pushes back, cold, neutral, dense. And at the boundary, there's a shock, a collision. The wind slams into the surrounding gas and heats up, glows. We can see this around some red giants, a faint shell of emission, evidence of the wind's interaction with space. And when the star finally dies, when it sheds its outer layers completely, that wind-blown material becomes a planetary nebula, a glowing cloud, lit from within by the hot core, beautiful, symmetrical, temporary. But we'll get to that later. For now, it's enough to know that the wind is constant, relentless. It's been blowing for millions of years, and it will keep blowing until the star has nothing left to give, until the outer layers are gone, until only the core remains. It seems as though red giants are generous. They give back to the universe more than they take. They create elements through fusion. They distribute those elements through winds. They enrich the galaxy. They make planets possible. They make life possible. And they do it quietly, without fanfare, just physics, just time. But the wind isn't the only thing happening. Deep inside, the star is changing again. The helium in the core is running out. The balance is shifting. And the next phase, the final phase, is about to begin. A phase of instability, of pulses, of thermal runaways that will shake the star to its foundation and begin the final unraveling. Stability is a luxury in the universe, and for a red giant, that luxury is running out. The helium in the core is nearly gone, burned into carbon and oxygen over 100 million years. And when the last of it fuses, when the fuel finally runs dry, the core goes quiet again. But this time, there's no gentle transition. This time, the star enters its most unstable phase, a phase of violent pulses, of thermal runaways, of chaos hidden beneath a deceptively calm surface. This is called the asymptotic giant branch, the AGB phase, and it's the final act. The star is no longer burning steadily. It's flickering, surging, dying in slow motion, but with sudden dramatic bursts of energy that shake the entire structure. Imagine a fire that's almost out, just embers, and then suddenly a gust of wind reignites it, a flare, bright and brief, and then it dims again. That's what's happening inside an AGB star, over and over, for hundreds of thousands of years. The structure is complex now. At the center, a core of carbon and oxygen, inert, dead. No fusion, just sitting there, held up by electron degeneracy pressure. Around it, a thin shell of helium, and around that, another shell of hydrogen. Two shells, both burning, both producing energy, but not steadily. The helium shell is unstable. It burns and pulses, and those pulses dominate the star's behavior. Here's how it works. The helium shell burns for a while. It fuses helium into carbon and oxygen, and as it burns, it dumps that ash onto the core below. The core grows, the helium shell gets thinner, and eventually the helium runs out again. The shell goes dormant, fusion stops, but the hydrogen shell just above it is still burning, and it's dumping helium onto the dormant helium shell. Slowly, steadily, layer by layer, the helium shell gets thicker, denser, hotter, and then, after maybe 10,000 years, maybe 100,000, the temperature reaches the ignition point again. 100 million degrees, and the helium reignites. But it doesn't reignite gently. It ignites explosively. This is called a thermal pulse, and it's one of the most dramatic events in a star's late life. In just a few years, sometimes just months, the helium shell burns through all the accumulated fuel. The energy output spikes, the temperature soars, the pressure rises, and the outer layers of the star expand rapidly. The star brightens. The radius increases by 10, maybe 20%, and then just as quickly it dims again. The pulse ends. The helium shell goes dormant, and the cycle repeats. Research shows that AGB stars experience hundreds, maybe thousands of these pulses over the course of a few million years. Each pulse lasts a few years. The time between pulses, the interpulse period, lasts tens of thousands of years. It's a stuttering, uneven process, not smooth, not predictable. Each pulse is slightly different, slightly stronger or weaker, slightly faster or slower, and each pulse has consequences. The energy from the pulse drives convection. Hot material from deep in the star rises to the surface. Cool material sinks. This is called dredge up, and it's important because the material being dredged up contains the products of fusion: carbon from the helium shell, nitrogen from the hydrogen shell, oxygen from the core, all of it mixed into the outer envelope, all of it visible in the star's spectrum. This is how carbon stars are made. Stars where so much carbon has been dredged up that it dominates the atmosphere, more carbon than oxygen. And when that happens, the chemistry changes. Carbon molecules form, carbon monoxide, cyanogen, acetylene, and dust, carbon dust. Tiny grains of graphite and silicon carbide. These grains are opaque, they block light. And when they block light, they're pushed outward by radiation pressure. They drive a strong stellar wind, and that wind carries away the star's outer layers. Some believe that AGB stars are the primary source of carbon in the universe. More than any other type of star, they produce it through fusion. They dredge it up through convection, they release it through winds, and over time that carbon becomes part of the interstellar medium, part of molecular clouds, part of planets, part of life. Let's talk about specific stars. Our Sculptoris is an AGB star about 1,500 light-years away, and it's fascinating. Observations with the ALMA telescope, the Atacama Large Millimeter Array, have revealed a spiral pattern in the gas around it. A perfect spiral, like a galaxy. But it's not a galaxy. It's the stellar wind shaped by the star's companion, a second star orbiting our Sculptoris, pulling the wind into a spiral as it moves. The pulses create shells, the companion creates the spiral, and the result is a geometric masterpiece, visible proof of the star's dying breaths. Then there's IRC plus 10216, one of the closest carbon stars, about 400 light-years away. It's surrounded by a thick shell of dust, so thick that the star itself is invisible at optical wavelengths. You can't see it with your eyes, but in the infrared it glows brightly. The dust absorbs the star's light and re-emits it as heat, infrared radiation. And we can study that. We can measure the temperature of the dust, the composition, the density, and we've found molecules, dozens of them, complex organic molecules, the building blocks of chemistry, all created in the outer layers of a dying star. And there's OH231.8 plus 0, 4.2, the Rotten Egg Nebula, an AGB star that's already starting to shed its outer layers. The wind is so strong that it's created two jets, streams of gas shooting out from the poles at hundreds of kilometers per second, and between them, a dense torus of dust and gas around the equator. It looks like a bow tie, or an hourglass, and it's glowing, faintly, lit by the central star. This is the transition, the moment between red giant and planetary nebula. The star is still pulsing, still losing mass. But the end is near. Scientists suggest that the pulses on the AGB are driven by a feedback loop. The helium shell ignites. It produces energy. That energy drives convection. Convection mixes material. The mixed material changes the composition of the shell. The changed composition affects the next pulse, and so on. Each pulse sets up the next one. It's a cascade, a chain reaction that gradually strips the star down to its core. Here's something people misunderstand. They think the AGB phase is calm because the star looks stable from the outside. The brightness changes, yes, but slowly, over months or years. Not violently, not explosively, but inside it's chaos. The pulses are violent, the convection is turbulent, the shells are unstable. The star is tearing itself apart from the inside out. And we can't see it. We can only infer it from models, from observations of the wind, from the changing spectrum. The mass loss rate on the AGB is extreme, much higher than during the earlier red giant phase. An AGB star can lose 1/10,000th of a solar mass per year, maybe more. In 1,000,000 years, 10% of the star is gone. In 5 million years, half. The star is evaporating, slowly but surely. And the wind carries away not just hydrogen and helium, but all the heavy elements: carbon, nitrogen, oxygen, silicon, iron, everything the star has made over billions of years, and the dust. The dust is everywhere. It forms in the cool outer layers: carbon grains, silicate grains, oxide grains. Each type of dust depends on the star's composition. Carbon stars make carbon dust. Oxygen-rich stars make silicate dust. And the dust affects the wind. It absorbs light. It gets pushed outward. It drags gas with it. The dust is the engine. The light is the fuel. And the wind is the result. One interesting detail is that AGB stars are also where certain elements are made that can't be made anywhere else. Elements like technetium. Technetium is radioactive. It has no stable isotopes. The longest-lived isotope has a half-life of about 4 million years. That's long in human terms, but short in cosmic terms. Any technetium that existed when the Earth formed has long since decayed. And yet we see technetium in the spectra of some AGB stars, which means it's being made right now in the star, through a process called the S process, the slow neutron capture process. In the S process, heavy elements capture neutrons one at a time, slowly, over thousands of years. Each capture makes the nucleus heavier, and eventually, after many captures, you get elements like barium, zirconium, and yes, technetium. These elements can't be made in the rapid explosions of supernovae. They need time. They need a steady supply of neutrons, and AGB stars provide that. The neutrons come from nuclear reactions in the helium shell, and they diffuse through the star, captured by heavy nuclei building complexity. This is how half the elements heavier than iron are made. The other half come from supernovae and neutron star mergers. But the S process elements, they're gifts from AGB stars, from these dying pulsating giants. And when the star sheds its layers, those elements are released. They mix with the interstellar medium. They become part of new stars, new planets, new worlds. Do you ever wonder what it would be like to watch an AGB star pulse from a safe distance, of course? Maybe from the orbit of a distant planet. You'd see the star brighten over a few years. The light would increase. The color might shift slightly. And then it would dim again. Slowly. Over decades. And then brighten again. A slow, rhythmic breathing. A cosmic heartbeat. Each pulse a little different. Each one bringing the star closer to its end. It seems as though AGB stars are caught between two states, still massive enough to hold themselves together, but not stable enough to burn steadily. They're in transition, becoming something else. And that transition is messy, chaotic, beautiful in its complexity. The pulses, the dredge up, the wind, the dust, all of it working together to dismantle the star piece by piece. And the time scale is short. Compared to the star's total life, the AGB phase is brief. Maybe 1,000,000 years, maybe 5,000,000. That's less than 1% of the star's total lifetime. A final flicker before the end. But in that flicker, the star accomplishes something remarkable. It creates elements. It enriches the galaxy. It prepares the stage for what comes next. Because the pulses can't last forever. Eventually, the outer envelope becomes so thin that the wind blows it away completely. The mass loss rate increases. The star loses more and more mass with each pulse. And finally, the envelope is gone, stripped away, scattered into space. And what remains is the core, hot, dense, exposed. A white dwarf in the making, but not yet, not quite, because the core is still surrounded by the remnants of the envelope, a glowing shell of gas, ionized by the core's intense ultraviolet radiation. And that shell, that expanding bubble of light, is about to become one of the most beautiful objects in the universe. Death can be beautiful. Not always. Not often. But sometimes, under the right conditions, when a star has given everything it has, when the last layers drift away and the core begins to glow, something extraordinary happens. A planetary nebula forms, a bubble of light in the darkness, symmetrical, glowing, temporary. The universe's way of saying goodbye. The name is misleading. Planetary nebulae have nothing to do with planets. The name comes from the 18th century. When astronomers first saw them through telescopes, they looked round and disc-like planets. Uranus, Neptune, pale and circular. So they called them planetary nebulae, and the name stuck. But we know better now. They're not planets. They're the outer layers of dead stars. Shells of gas ionized and glowing, expanding into space at tens of kilometers per second, and they're everywhere. There are thousands of them in our galaxy, maybe tens of thousands, each one unique, each one a snapshot of a star's final moments, and each one breathtakingly beautiful. Let's start with the most famous one, the Ring Nebula, M57, in the constellation Lyra. It's about 2,000 light-years away, and it looks exactly like its name suggests. A ring, a donut of glowing gas, green and blue on the inside, red on the outside. At the center, a tiny white dot, the white dwarf, the core of the star that created it, hot, dense, dying slowly. The Ring Nebula is about 1 light-year across. That's the distance light travels in a year, about 6 trillion miles. And it's expanding, growing, at about 20 kilometers per second. In another 10,000 years, it'll be twice as large, fainter, more diffuse. And eventually, in a few 100,000 years, it'll fade completely. Dispersed. Mixed with the interstellar medium. Gone. Scientists suggest that the Ring Nebula formed about 6,000 years ago. That's recent, in cosmic terms. While humans were building the first cities, inventing writing, the star at the center of the Ring Nebula was shedding its outer layers. And the light from that event, that final exhalation, is just now reaching us. But not all planetary nebulae are rings. Some are spheres, some are bipolar, some are irregular. The shapes depend on several factors: the star's rotation, magnetic fields, companion stars, the density of the surrounding medium. Each factor adds complexity, and the result is a gallery of forms: circles, ellipses, hourglasses, butterflies, spirals. The Helix Nebula is another famous example, NG C7293. It's one of the closest planetary nebulae, about 650 light-years away. And it's huge, 2.5 light-years across, so large that if you could see it with your naked eye, it would cover an area of sky half the size of the full moon. But it's faint. Very faint. You need a telescope. And even then, it looks ghostly. A pale ring, almost translucent. The helix is sometimes called the Eye of God, because it looks like an eye, a blue-green iris, a red outer ring, and a white pupil at the center. The white dwarf, staring out at the universe, unblinking. It's evocative, haunting, and completely natural. Just physics, just gas expanding and glowing. Then there's the Cat's Eye Nebula, NGC 6543, about 3,000 light-years away. And it's complex, incredibly complex. At the center, a bright oval, surrounded by concentric shells, layers and layers of gas, each one ejected at a different time, each one representing a pulse, a thermal runaway, a moment when the star shed mass. And around the shells there are jets, streams of gas shooting out from the poles, and filaments, tendrils of gas stretching outward, twisted, knotted, shaped by magnetic fields and stellar winds. Research shows that the Cat's Eye Nebula has at least 11 concentric shells. 11, each one separated by about 1,500 years, which suggests that the star pulsed regularly. Every 1,500 years, it shed a layer, for tens of thousands of years, and we can see the result, a nested structure like Russian dolls, or the rings of a tree, a record of the star's final breaths. One common mistake is thinking planetary nebulae are static, frozen, but they're not. They're dynamic, expanding, changing. We can measure the expansion, we can track the motion of the gas, and in some cases we can see changes over decades, knots of gas moving, filaments brightening or dimming, the nebula evolving in real time. The Hubble Space Telescope has been invaluable for this. It's observed planetary nebulae for decades, and by comparing images taken years apart, astronomers can see the motion, the growth, the transformation. It's like watching a flower bloom, slowly, over years, but visibly. So, what makes them glow? Why are they so colorful? It's all about ionization. The white dwarf at the center is hot, extremely hot. Surface temperatures can reach 100,000 degrees Celsius, maybe more. That's 20 times hotter than the sun. And at that temperature, the star emits a lot of ultraviolet radiation, high-energy photons, and those photons hit the surrounding gas. They strip electrons from atoms, ionize them, and when the electrons recombine when they fall back into their atoms, they emit light, specific wavelengths, specific colors. Hydrogen emits red light, H-alpha, at 656 nanometers. Oxygen emits green and blue-green light, O3, at 496 and 501 nanometers. Nitrogen emits red. Sulfur emits red. And when you combine them all, you get the colors we see, the reds and greens and blues. Each color tells you what elements are present. Each hue is a fingerprint of chemistry. And the shapes, the symmetry. Why are so many planetary nebulae so perfectly round or so perfectly bipolar? Some believe it's because of binary stars, companion stars. Many, maybe most stars are part of binary systems. Two stars orbiting each other. And when one of them becomes a red giant, the companion affects the mass loss. It shapes the wind. It can create jets, disks, spirals, all the complex structures we see. The Butterfly Nebula, NGC 6302, is a perfect example. It's bipolar, two lobes extending in opposite directions, like wings. Each lobe is about 3 light-years long, and they're moving, fast, at hundreds of kilometers per second, faster than most planetary nebulae. The gas is being ejected in jets, collimated streams, focused by something, maybe a disk, maybe a companion star. We don't know for sure, but the structure is unmistakable and beautiful. Then there's the Eskimo Nebula, NGC 2392. It looks like a face, a round center, a bright ring, and an outer halo of filaments that look like fur, or a parka hood, hence the name. It's one of the more complex structures, layers within layers, and we've studied it closely. The central star is a binary, two white dwarfs, orbiting each other. And that binary system shaped the nebula, created the symmetry, the layers, the filaments. Scientists suggest that planetary nebulae only last about 10,000 to 50,000 years. After that, they fade, the gas disperses, the central star cools, and the nebula becomes invisible, integrated into the interstellar medium. No longer a distinct object, just part of the background. And that's okay. That's the point. Planetary nebulae are not meant to last. They're meant to recycle, to return material to space, to enrich the galaxy. And the material they return is precious. Carbon, nitrogen, oxygen, all forged in the star's core, all dredged up during the AGB phase, all released in the final mass loss, about half a solar mass of enriched gas, scattered across light years, ready to be incorporated into new stars, new planets, new life. Here's something to think about. Every planetary nebula was once a red giant, and every red giant will, if it's the right mass, become a planetary nebula. It's the natural endpoint, the final stage, the moment when the outer layers are finally blown away and the core is revealed. And for a brief time, maybe 10,000 years, the nebula glows, lit from within by the dying ember of the star. Do you ever wonder what our sun's planetary nebula will look like? What shape it will have? What colors we can guess? Based on the sun's mass, its rotation, its composition. It will probably be fairly round, maybe slightly elliptical, green and red, oxygen and hydrogen, expanding slowly, fading over tens of thousands of years. And at the center, a white dwarf, the size of Earth, the mass of the sun, cooling over trillions of years. It seems as though planetary nebulae are the universe's art, created not by intelligence, not by design, but by the same forces that shape everything else: gravity, radiation, chemistry, and the result is beauty, symmetry, color, light emerging from death, not as a contradiction, but as a continuation. And the central star, that white dwarf, it's not truly dead. Not yet. It's still radiating, still glowing, still incredibly hot. But it's no longer fusing, no longer creating energy. It's just cooling, slowly, over billions and billions of years, a fading ember in the cosmic dark. And around it, the nebula expands, a monument, a memorial, a brief flash of light before the silence. But the story doesn't end with the nebula fading, because the white dwarf remains, and the legacy of the red giant, everything it created, everything it released, drifts onward through the galaxy, waiting, ready to begin again. And in that waiting, in that quiet persistence, there's a lesson worth remembering. There's a kind of peace that comes from knowing how things end, not the surprise, not the shock, but the slow, inevitable conclusion, the final note of a song that's been playing for billions of years. Red giants don't explode. They don't tear the fabric of space. They just breathe out one last time and let go. And in that letting go, they leave behind something far more valuable than fireworks. They leave behind us. Let's step back for a moment. Let's think about what we've journeyed through. A star is born from a cloud of gas, mostly hydrogen, a little helium, a trace of heavier elements left behind by previous generations. It contracts under gravity. It heats up. And when the core reaches 15 million degrees, fusion ignites. Hydrogen becomes helium. Energy floods outward. The star inflates, stabilizes. And for billions of years, it burns. Our sun has been doing this for 4.6 billion years. Steady, reliable, pouring out light and heat, warming planets, making life possible on at least one of them. And it will continue for another 5 billion years, maybe a little more, maybe a little less. The calculations are close, but the end point is certain. When the hydrogen in the core runs out, the sun will change. The core will contract. The outer layers will expand. The sun will become a red giant. It will swell past Mercury, past Venus, maybe to Earth's orbit. The surface will cool, the color will shift to red, and for 1 billion years, give or take, the sun will exist in this new state, larger, cooler, more luminous, but fundamentally different. And then the helium will ignite, the core will flash, briefly, violently, hidden beneath layers of gas, and the sun will settle into a second phase of fusion. Helium burning in the core, hydrogen burning in a shell, a temporary stability, 100 million years of grace. But helium, like hydrogen, runs out. And when it does, the sun will enter the asymptotic giant branch, the AGB phase, pulses, thermal runaways, dredge up, mass loss. The outer layers will be blown away by stellar winds. Carbon and oxygen will be scattered into space. And finally, when the envelope is gone, the core will be exposed. A white dwarf, hot, dense, no longer burning, just cooling. Forever. And around it a planetary nebula will glow for 10,000 years, maybe 20,000. A shell of gas, ionized, luminous, beautiful. And then it will fade, disperse, become part of the interstellar medium. And the white dwarf will remain, alone, cooling over trillions of years, longer than the current age of the universe, slowly, quietly, until it's just a cold, dark sphere, a black dwarf. Though no black dwarfs exist yet, the universe isn't old enough. This is the fate of every star like the sun, and most stars are like the sun, or smaller. The universe is full of red dwarfs, M-type stars. They're even more common than sun-like stars, and they'll live even longer, tens of billions of years, hundreds of billions. Some of them will outlive the universe as we know it, but eventually they too will die. They'll become white dwarfs, skip the red giant phase entirely, too small, too slow, but still the same endpoint. Research shows that about 90% of all stars will end as white dwarfs. The other 10%, the massive ones, will explode as supernovae. They'll create neutron stars or black holes, violent, dramatic, but rare. Most stars die gently, like red giants, like the sun. And that gentleness is important, because gentle deaths enrich the galaxy without destroying it. Think about the elements. Hydrogen and helium came from the Big Bang. Everything else came from stars. Carbon, nitrogen, oxygen, silicon, iron, all forged in stellar cores, all released when stars die. Supernovae contribute. Yes, they're spectacular. They create elements heavier than iron, gold, platinum, uranium, but the everyday elements, the ones that make up planets and life, those come mostly from red giants, from AGB stars, from planetary nebulae. Every breath you take contains oxygen from a red giant. Every thought you have depends on carbon from a red giant. Every beat of your heart is powered by chemistry that wouldn't exist without stars that lived, evolved, and died billions of years ago. You are quite literally made of stardust. Not poetically, not metaphorically, literally. The atoms in your body were forged in the cores of dying stars. And that's not just beautiful, it's humbling. Some believe this connection, this atomic ancestry, should change how we see ourselves. We're not separate from the cosmos, we're part of it. We're a way for the universe to know itself, to look back at its own history, to wonder, to ask questions. Why are we here? Where did we come from? What happens next? And the answers, all of them, lead back to stars. Let's talk about the future, not just the sun's future, but the universe's future. In 5 billion years, the sun becomes a red giant. In 10 billion years, it's a white dwarf. But what about other stars? What about the red dwarfs? The ones that will outlive everything. The smallest red dwarf stars, with about 8% the sun's mass will burn for 10 trillion years. That's 1,000 times longer than the current age of the universe. By the time they die, the universe will be unrecognizable. Most galaxies will have merged. Most stars will have burned out. The cosmic microwave background will have cooled to nearly absolute zero. And those last red dwarfs, the final stars, will be the only sources of light in a cold, dark universe. And when they die, when they finally exhaust their hydrogen and become white dwarfs, the era of stars will end. No more fusion. No more light from stars. Just the slow cooling of white dwarfs, the decay of protons, the evaporation of black holes, the heat death of the universe, entropy, maximum. Everything cold, everything dark, everything still. But that's trillions of years away. For now, the universe is young, vibrant, full of stars, and red giants are part of that vibrancy. They're the elders, the wise ones, the ones who've lived long enough to see the universe change, and they're giving back, enriching, teaching, preparing the next generation. Scientists suggest that the Milky Way produces about one planetary nebula per year. Somewhere in our galaxy right now, a red giant is shedding its outer layers. Somewhere a white dwarf is being revealed. Somewhere a nebula is beginning to glow. And we can see them, we can study them, we can learn from them, and we have. The study of planetary nebulae has taught us about stellar evolution, about nucleosynthesis, about the life cycle of matter. It's shown us that the universe recycles, that nothing is wasted, that death is not an end but a transformation. And that's a lesson worth holding on to. Here's something to consider. The sun will become a red giant. Earth will be destroyed, or at least rendered uninhabitable. But by then, humanity, if it still exists, will have spread. We'll have moved to other star systems, other planets, other galaxies, or we'll have evolved into something we can't even imagine, something adapted to the universe as it will be, not as it is now. And maybe some distant descendant of humanity will look back at the sun, at the white dwarf it's become, at the faint planetary nebula around it already fading. And they'll remember, they'll know that this was where it started, this was home, and they'll feel gratitude, not sadness, because the sun's death will have made their existence possible. The carbon in their bodies, the oxygen they breathe, all gifts from a star that learned to let go. Do you ever think about legacy? About what you'll leave behind, red giants leave behind, elements, planetary nebulae, white dwarfs, and the memory encoded in the chemistry of the galaxy that they were here, that they mattered, that they contributed. It seems as though the universe has a way of honoring its past, not with monuments, not with words, but with continuation. The cycle never stops. Gas becomes stars, stars become elements, elements become planets, planets become life, life becomes thought, thought becomes questions. And questions lead us back to stars, full circle. The red giant phase is not a tragedy. It's a transition, a necessary step in the cosmic story. Without red giants, there would be no heavy elements, no planets, no life, no us. They're not dying failures. They're successful completions, stars that did their job, burned their fuel, created complexity, and gave it back. And there's something deeply comforting about that. The idea that the universe doesn't waste anything, that every atom, every particle, every bit of energy is reused, recycled, reformed. The hydrogen in your body was made in the Big Bang. The carbon was made in a red giant. The iron in your blood came from a supernova. You are a collaboration, a cosmic effort, billions of years in the making. So when you look up at the night sky and you see a reddish star, think about what it is. An elderly sun, a giant, gentle, generous, dying slowly, creating elements, enriching the galaxy, preparing for the next generation. And know that our sun will join them, not soon, but someday. And when it does, it will do the same. It will give back. It will contribute. It will complete its journey. The story of red giants is not a story of endings. It's a story of transformation, of giving, of legacy. And in that there's beauty, there's meaning, there's a kind of immortality, because the atoms they create will live on, in stars, in planets, in beings yet to come. And the light they emit even now is traveling through space, reaching us, touching us, connecting us to the past and the future. We've drifted through the life and death of stars tonight, through fusion and expansion, through pulses and winds, through planetary nebulae and white dwarfs. And through it all, one thing has remained constant. The universe is not random. It's not chaotic. It's governed by laws, physics, chemistry, mathematics. And those laws, predictable and beautiful, give rise to everything. To stars, to planets, to life, to you. Thank you for staying with me through this quiet journey, for listening, for wondering, for allowing yourself to drift through the cosmos slowly, gently, with curiosity as your guide. The stars are still out there, still breathing, still evolving, and there are so many more stories to tell. Stories of neutron stars and black holes, of galaxies and dark matter, of time and space and the very fabric of reality. And when you're ready, when the night calls you back, those stories will be here, waiting, just like the stars. Sleep well, dream gently, and remember, you are made of stars, and the stars, even the dying ones, are still shining, still giving, still beautiful. Good night.